Hello everyone, this is Aniket here. Here we are going to study the superconductivity of H3S at 203 Kelvin. Myself Aniket from IIT Kanpur, the Department of Physics. So firstly we will start with the abstract. As we all know, superconductor is the material which has almost zero resistance. This happens as we cool the material. Resistance of material drops to zero. The temperature below which this happens is we called superconducting transition material temperature. The highest the transition temperature that we achieved till now is 133 Kelvin. At some condition that is at ambient pressure now, and 164 Kelvin at high pressure in copper oxide we got superconducting state. So there is no bound to get upper transition temperature theoretically. So for doing so, we need the combination of high frequency phonons, strong electron phonon coupling, and high density of state. This condition can be fulfilled in principle. So for metallic hydrogen, some calculation predict that the TC or the transition temperature for hydride is in the range 50 to 235 Kelvin, but only at moderate TC we has been observed experimentally. Our assumption is that a metal with transition temperature should have strong covalent bonding with high frequency mode in phonon spectrum. This above condition gives such an environment for searching material having high transition temperature. Okay, so that's the thing that we are looking for. Now the second term is introduction. So here we are interested to know the superconductivity of material at a relatively higher temperature as we found in other material. So in this paper we are interested in studying the sulfur hydride at T transition temperature equals to 8 Kelvin as we apply a pressure of around 90 gigapascal. Here we are discussing the superconductivity of H3S formed. This can be formed from H2S by decomposing under such a pressure as we mentioned above. Okay, so these are the steps towards achieving room temperature superconducting material. We choose H2S as our material of interest because it is easy to handle and behave as a superconductor at low pressure also, and it's about 100 gigapascal, and the critical that transition temperature equals to 80 Kelvin. Hydrogen sulfide transform into a metal at 96 gigapascal as a theory that we called BCS theory doesn't have any upper limit on TC. Okay, so based on the calculation, metallic hydrogen should be a superconductor at very high TC. It about up to 240 Kelvin for the metallic hydrogen. Okay, and 300 to 350 Kelvin in atomic phase at 500 gigapascal. Lower pressure are required to metallic hydrides in comparison to pure hydrogen. Therefore, we chose H2S. Then there is a temperature dependence of resistance for sulfur hydride. Okay, at different temperature, the resistance of H2S depends on temperature. At first, sample is set at T equals to 200 Kelvin and pressure is at about 100 gigapascal. The sample is cooled down to 4 Kelvin. After warming to 100 Kelvin, pressure was further increased. Then the resistance was measured with 10 microampere current. We will see the graph in the result section. Okay, after result section. So the next term is methodology, that what we done. So to measure the resistance of material we use diamond anvil sails. It's of diameter 200 to 300 micrometer at 7 to 8 degree to the cutlet of 40 to 80 micrometer to separate the metallic gasket of T301 stainless steel of 250 micrometer thick placed at near about 19 gigapascal. A layer was formed by pressing the insulating material on imprint. That imprint was drilled at the bottom. Insulating material does not react with H2S. Therefore, this layer is drilled to form a hole. Four titanium electrode were deposited on diamond anvil. Then the gasket was put on the anvil. So the DAC was placed into a cryostate and cooled down to 200 Kelvin. The H2S gas was put into a capillary into the rim around diamond anvil. So then the sample was identified by measuring Raman spectra. Then liquid H2S was clamped in a gasket hole. Interference pattern gives the thickness of the sample, and it is about near about few micrometer. So DHC was heated to 220 Kelvin to evaporate rest of the H2S. Okay, the pressure was determined by the diamond scale at room temperature and low temperature. So to prepare sample with high TC, low temperature is required. Okay, so we place H2S at a room temperature sample and it decomposes before reaching high pressure phase of H3S. Therefore, the resistance. So the thing is, key the resistance were measured during the pressurizing using four probe Vander Pau method with 10 to 10,000 microampere current. The influence of magnetic field on the superconducting transition has been measured with non-magnetic DAC. Okay, we will gonna see now results what we get. So due to the fact that difference in temperature depends ZFC and FC magnetization, this material is of second type. Then the graph shows that it's a superconductor with mixed state. The third one is we find the limit in coherence length from 2 nanometer to 2.3 nanometer. London penetration depth can be calculated using the relation between lower critical and upper critical field. Then accordance to the Bean's model, magnetic critical current density can be calculated from distance between the direct and returning branches. Okay, so the next is the temperature dependence of resistance that we discussed earlier. There is a graph only. So another there are also some graphs which shows temperature resistance versus temperature graph, resistance versus pressure graph. So the next thing is discussion. So in superconducting state, the magnetic moment for the disk is calculated by the formula magnetic moment of disk equals to zero point 0.2 r cube into h. Here the h is magnetic intensity for a disk of radius 40 micrometer and magnetic intensity is near about 2 milli Tesla. Then the magnetic moment is calculated as 2.6 into 10 to the power minus 7 EMU. This is the unit. Okay, using this calculation, the signal can be detected. A high pressure DAC made of Cu, copper. The sulfur hydride sample is not seen. The background signal acquired in the normal state as shown above. Okay, so we will move to the conclusion part. In this manner, okay, we had observed the superconducting property of metallic sulfur hydride at 203 Kelvin temperature. We got the temperature and resistance dependent graph. Magnetic susceptibility was measured. These are the steps towards getting room temperature superconducting material that we are interested to found that. Okay, we find that. So that's the thing. Then we have acknowledgement, then we have some references from where we from where I prepare this slide PowerPoint. So thank you.